This video is a summary of the fifth topic of the specification of AQA GCSE Chemistry, which is the last topic that comes up in Chemistry Paper 1. You might find it a useful video if you're getting ready for an end of topic test or if you're preparing for your GCSE Chemistry Paper 1. We look at exothermic and endothermic reactions, the required practical that comes up in this topic, calculations using bond energies, and then finally chemical cells and fuel cells just for the triple scientists. In order to understand the energy changes topic, it's important that you know the law of conservation of energy. This tells us that energy is conserved in a chemical reaction. This means that no energy is created and no energy is destroyed. You should be able to classify chemical reactions into two types. The first type is exothermic. Ex means out, like an exit or being extroverted, and therm is to do with energy. So exothermic reactions transfer energy out to the surroundings. In practical terms, what this means is that they tend to heat them up. Examples of exothermic reactions include combustion, otherwise known as burning a fuel in oxygen, many oxidation reactions, and neutralization. You should be able to identify all of these as exothermic reactions which would raise the temperature. As well as naming specific chemical reactions that are exothermic, you should be able to identify some uses of them. Specifically in self-heating cans, the kind of things that you can take camping with you so that you can warm food up without needing a fire, and also hand warmers, those little jelly packets that have a metal disc in them that you click and then it goes hard and solid and also very hot. The opposite of an exothermic reaction is an endothermic reaction, one that takes in energy from the surroundings and therefore in practical terms tends to cool them down. The two named examples of endothermic chemical reactions in the GCSE chemistry specification are thermal decomposition. So decomposition means breaking something down and thermal means using heat energy. So this could be something like heating up copper carbonate until it breaks apart to make copper oxide and carbon dioxide. And then also the reaction of citric acid and sodium hydrogen carbonate. One endothermic reaction that isn't listed in your specification but that you're probably also very familiar with is photosynthesis, although this takes in energy in the form of light radiation rather than heat energy. Your named use for endothermic chemical reactions is sports cool packs. The required practical for Unit 5 is incredibly broad. You're asked to investigate the variables that affect the temperature change of reacting solutions, but there isn't further detail given than that, so there are lots of different chemical reactions that you could have done, and any of these could be asked about in the exam. Common reactions would include neutralization, where you're mixing together an acid and an alkali, or some kind of displacement reaction, for instance where you're adding different metals or different masses of metals to a solution of copper sulfate. Regardless of the specific reaction that you ended up doing, there are some common themes throughout. The first one is that you're going to measure the temperature change, so you'll be using a thermometer. And the reason for doing this is so that you can determine whether the reaction is exothermic or endothermic, and also determine how exothermic or how endothermic. So if the temperature rises, it's exothermic, and if the temperature falls, it's endothermic. Another common feature is that because we want the temperature change that we're measuring to be as large as possible, we don't want energy transfers out to the wider atmosphere. So for this reason, when you do the experiment, you will insulate it, usually by carrying it out in a polystyrene cup, potentially with a lid. You might be asked about how you could improve the precision of your experiment. And to do this, you would probably want to use a digital thermometer, because generally speaking, these are more precise. If you're using a regular alcohol thermometer, you can probably only determine the temperature to the nearest degree. That's what we would call the resolution, whereas the resolution of a digital thermometer is often to the nearest tenth of a degree. Whatever the experiment you're carrying out is, you need to consider your control variables, because without control variables, the experiment won't be valid. So in the scientific method, if we're trying to investigate a question and we're trying to determine does a particular independent variable affect the dependent variable and by how much, we need to control anything else that might also affect the dependent variable. So for instance, if I was going to add different metals to some copper sulfate solution, it would be really important that I added the same mass of each metal, and that I also maintained the same volume of the copper sulfate solution and also the same concentration. If you're asked to write a method, and this would be quite a common 6-mark question, it's important that you actually discuss changing the independent variable and, if relevant, talking about how you would do that. So for instance, if you're changing the concentration of some copper sulfate solution or some acid, you could describe how you would measure out different volumes of that solution and then dilute it with water. One little side note here about vocabulary. In chemistry, we often see people referring to the amount of metal they would add or the amount of copper sulfate that they would use. And this can be problematic because in chemistry, amount has a very specific meaning. It refers to the number of moles of a substance that you have. So particularly when you're talking about a solution like an acid or like copper sulfate, where you're changing the concentration, it's not accurate to talk about keeping the amount the same because you're not. So it's much better to avoid the word amount completely. And if you're talking about a solid, refer to the mass you're adding. And if you're talking about a solution, talk about the volume. This required practical also represents a really good opportunity for AQA to assess your math skills. Remember, the mathematical requirements of the GCSE chemistry paper have to make up 20% of the marks overall. This includes skills like selecting an appropriate graph, plotting variables, and also translating data between graphical and numerical form. In other words, can you plot the data and can you read values off a graph that has already been drawn for you? One thing that often confuses students is what type of graph they should be drawing. If I carried out an experiment where I added different metals to a solution of copper sulfate solution, then I would draw a bar chart. And the reason for this is that here my independent variable is categorical. So tin is completely separate to magnesium. They're not on a scale, they're not numerical values where I could have any value, they're distinct categories. So therefore I have to draw a bar chart. When I'm thinking about drawing that bar chart, I obviously want to be drawing it with a ruler, and I want to make sure that my bars are the same width. I also want to make sure that there are gaps between the bars, and this is because those different data points are completely independent of each other. If, on the other hand, I did an experiment where I was reacting together some solutions and I was changing the concentrations of those solutions, then I would draw a scatter graph, and this is because my independent variable is continuous. In other words, within a range, my independent variable could be any value. So here I've got concentrations of 0.2 and 0.4 and 0.6, but I could also have a concentration of 0.5 or 0.52 or 0.521. Any value in that range will be valid. So this is continuous data, and therefore I need to draw a scatter graph, and therefore I could have a line of best fit that goes through it. Regardless of whether you're drawing a bar chart or a scatter graph, it's important that we make sure that our scales are even. So in other words, if you look at my x-axis of the right-hand graph, you can see it's going up in 0.2s. I haven't sort of gone 0.2, 0.4, and then suddenly switched to 0.5, 0.6, 0.7. It's also really important that we make sure that we've labelled our axes, and when we do that, we've also labelled them using the units. To understand the next couple of bits about reaction profiles and also bond energy calculations, it's important that we understand that chemical bonds are a store of energy. And so breaking those bonds requires even more energy to be put in, whereas forming those bonds is going to release energy. And different bonds require different amounts of energy to break. So if I give you the names of any two elements that might have a bond between them, there's a specific value for how much energy it's going to take to break that bond. Quite a common question in recent years has been to ask you to either label or draw from scratch a reaction profile. So this is showing us about the amount of energy that is stored in the chemical bonds of the reactants and the products. So to start with, I'm going to have a horizontal line which is labelled with the reactants. If I know what the reactants are for the particular question, then I should be writing those words. But if I don't, I could just write the word reactants. Now, this is going to be an exothermic reaction to begin with, so therefore when I draw my horizontal line for the products, it's going to be lower. Now that can be a little bit confusing for people because they think, well, hold on, exothermic reactions, that's about giving out energy. But if you think about it, if energy has been given out to the surroundings, then what's left in the product is going to be less. We've kind of spent some of the energy. Now, one thing you may be asked to do is to label the overall energy change. So what I'm going to do is do some little dotted lines across from my reactants and my products, and the overall energy change goes between those. So in this instance, the energy that is in my reactants has gone down to the energy that's in my products. We've had a decrease. Once I've drawn that, I can carry on with the rest of the reaction profile. So this is going to go up before it goes down, and that's always the case, because what's happening is I'm putting in energy in order to break the bonds in the reactants, and you're always going to have to put in an amount of energy to start the reaction. So we're always going to go up to a point that's called the transition point or the transition state. So then I'm going to label my activation energy, and that's going to go up from the height of the reactants to the peak. So that's my exothermic reaction. My endothermic reaction is also going to start with a horizontal line labelled either with the word reactants or the name of the reactants if I know them. But because this is an endothermic reaction rather than an exothermic reaction, the overall energy in my products at the end is going to be higher because they've absorbed energy from the surroundings and now they have more energy. Once again, to label my overall energy change, I'm going to do dotted lines that go across from the reactants and products, and the overall energy change is between them, always going from reactants to products. So you can see that for my exothermic reaction it went down, but for my endothermic reaction it's gone up. Then I can do the rest of my profile, so again it's going to go up before it comes down because that's about the energy that is being absorbed to break the bonds, and then the activation energy is going to be labelled between the reactants and the peak, the transition point. As we said before, different atoms require different amounts of energy to break the bonds between them, and we can put those values together with a balanced symbol equation in order to calculate the overall energy change for a reaction, and therefore figure out whether it's exothermic or endothermic. Here's a simple reaction involving 2 moles of hydrogen reacting with 1 mole of oxygen to produce 2 moles of water. Now the first thing that I would do, and to be honest this is such a simple example that we don't need to do it, but it's a good habit to get into, is I would redraw the diagrams that they give you so that I actually have my 2 hydrogen molecules and my 2 water molecules, because this is going to stop me from making silly mistakes later on. So now that I have a picture that accurately represents what I'm going to do in this reaction, I need to think about which bonds are going to need to be broken and which bonds are made in the reaction. On my exam paper, I would physically cross out the bonds that are being broken and write down the values of those bonds. So that's 436 for each of the hydrogen-hydrogen bonds and 498 for the double bond between oxygen. This gives me a total value for bonds being broken of 1,370 kilojoules per mole. Now I can think about the bonds being made, and again here I would physically cross them out or highlight them in green, because this means that when I go back and check I can make sure that I haven't missed out any bonds. Obviously this is a very simple question, but sometimes you're going to get much more complicated molecules and it's really easy to miss out one of the bonds in the middle. So here I've got 4 oxygen-hydrogen bonds, and I absolutely could write 4 times 464 instead, but my preference is to write down the individual value as you cross out each bond. This gives me a total value of 1,856. For the GCSE exams, somewhat strangely, AQA don't actually expect you to know which way round to do the calculation. They just expect you to look at the numbers and say, oh, this one is bigger, therefore. But particularly if you're looking at going on and studying chemistry further, I think it's worth knowing how to do it properly. So all we're going to do is put a minus sign in the middle of the page. So we're going to do our energy taken in, which is 1,370, subtract our energy released, which is 1,856. And if I do that, then I get a negative number, and the negative number tells me that this is exothermic. I could also work that out just by looking at the numbers and comparing the size of them, seeing that more energy is given out when making bonds than is taken in when breaking them. But personally, I think that doing it mathematically and looking for a negative number is just much easier. In the last couple of years, AQA have moved on from just asking you to calculate the overall energy change, and they've had a couple of questions where they give you the overall energy change and then ask you to work out the value of a particular bond. And this can be particularly challenging because, as I've said, they don't expect you to know how to do the calculation and know that a negative value is exothermic. So instead, they phrase it quite weirdly, in my opinion, and they sort of tell you that the energy needed to break the bonds or make the bonds is this much bigger. So you have to kind of think your way around it a little bit. But anyway, here's an example of this kind of question. So we've been given the values for the hydrogen-sulfur bond and the oxygen-oxygen double bond and the hydrogen-oxygen bond, but not the sulfur-oxygen bond. So that's the one that we're going to have to calculate. So the first thing that I would do is I would draw out all of your molecules so that, again, we can cross out those bonds as we're going through. And that's going to avoid a situation where you forget that you need to apply that coefficient to everything that comes after it, which is a really, really common mistake that we see. So then I'm going to write myself an overall equation that includes the value of 1034 and also just includes x or something like x for the bond that I don't know about. So I'm going to have 4 lots of 364, in other words, 4 hydrogen-sulfur bonds, and 3 lots of 498, so that's 3 oxygen-oxygen bonds. Take away everything on the right-hand side. So everything on the right-hand side is going to be 4 lots of 464 for my 2 water molecules and 4x for my 4 sulfur-oxygen bonds. And all of that lot together gives me a value of minus 1034. Because we've said that the energy needed to break the bonds is 1034 less than the energy released. So the right-hand side, that 4 times 464 plus 4x, must be 1034 bigger, and therefore that's going to give me a negative number when I do that subtraction. So now I'm going to multiply out all of these values, and I'm going to have 2,950 on the left, and then 1,856 plus 4x. So then I can simplify this further and I get a value of 2,128 for 4x, and then I divide by 4 to get my final value for x, which is the value of the sulfur-oxygen bond. The last part of this video about chemical cells and fuel cells is only for GCSE chemistry students. So in other words, triple scientists. If you're doing combined science, then you're done. So if you're doing triple science, you should know that cells contain chemicals that react with each other to produce electricity. And the particular voltage that's produced by a cell is dependent on a number of factors, including the type of electrode and also the electrolyte. So we could do a number of different experiments where maybe we change the metal of the electrodes and see how that affects the voltage, or we change the concentration of the electrolyte and see how that affects the voltage. Either way, you can create a simple cell by connecting together 2 different metals that are in contact with an electrolyte. So the easiest way you can do this if you're teaching it just to year 7s is to stick 2 different kinds of metal into a lemon, and then you can form a cell that way. But either way, we need 2 different kinds of metal, because the reason that this works is the difference in reactivity between the electrodes. So if you had exactly the same electrode twice, then you wouldn't have any potential difference. Interpreting data tables from investigations where you're making chemical cells can be quite a headache, and in fairness to AQA, the last couple of times they've assessed this, they have simplified it, maybe because they've realised this is just more than a lot of students can cope with. But I think it's worth us looking at kind of the most complex data they could give you, and that way you're prepared for every eventuality. So a table like this is designed to show you what is the voltage being measured when we have different pairs of electrodes. So you've got electrode number 1 along the top and electrode number 2 down the side. Now the first thing you'll notice is that we've got this greyed out bit on the right hand side, and that's because there's no point in measuring the same pair of electrodes twice just the other way round, because we know that the voltage will be the same magnitude just with the opposite sign. So if it's 3.2 between magnesium and silver, between silver and magnesium it would just be minus 3.2, and there's no point doing the experiment. And then the second thing you'll probably notice is that we've got this diagonal here where all the values are 0. And that's because, as we said, we won't get any voltage happening if we've got 2 electrodes that have the same reactivity. The size of these values is going to correspond to the reactivity of the metals, and it allows us to put them in order of reactivity. It is important whether the value is positive or negative. So one is going to be more reactive and one is going to be less reactive than the electrode you're assessing it against. But there isn't a way that you can just figure this out on the fly. So what you need to do is pick one of the metals that you know is very reactive or very unreactive and work it out from there. So if I look at my first column, I know that magnesium is a very reactive metal. So in this particular table, I can therefore work out that a negative number corresponds to the metal on the left being more reactive than the metal up the top. And I can see here that silver, which I know is very unreactive, has a positive value. Okay, so that's something that you're going to have to work out on a case-by-case basis. But once I know that, I can work out some things about the other metals that I might be less sure of. So I might not actually know where tin goes in the reactivity series, but now I've seen that magnesium has a negative value and I know that that's more reactive, I can work out that iron and zinc also must be more reactive than tin. So I can use this to put all of these metals into an order of reactivity. So in this instance, my biggest difference, my most negative value in this case is magnesium, so that's going to be my most reactive, followed by zinc, followed by iron, followed by tin, followed by silver, which in that first column is the only thing that is positive, so it's the only thing that's less reactive than tin. Now, the other thing that you may be asked to do is to work out what the value would be of something that hasn't been measured. So here you can see I've got the blue box and I've called it X, that's what that is. Now, this can take a little bit of getting your head around, but I think the fastest way to do it is to just get everything on a number line. So I'm going to draw a number line and I'm going to compare everything to the most reactive metal. So if I compare magnesium to magnesium, that's giving me a value of 0. If I compare silver to magnesium, that's giving me a value of 3.2. So I can put each of these onto my number line. And obviously for tin, I have to think a little bit carefully and go, well, I haven't got tin in the magnesium column, but if I did, it would be the negative of the magnesium in the tin column, so it would be 2.3. So now if I compare any two of these metals, I can work out what the value in the table would be. So let's start off with something that is in the table so that you can check that I'm right. So if we compare silver to zinc, silver is at 3.2 and zinc is at 1.6. So to go from silver to zinc, I go down by 1.6, and that's exactly what I've got in the table. I've got a value of minus 1.6. So if instead of going from silver at 3.2 down to zinc at 1.6, I go from iron, which is at 2, down to 1.6, then I've only gone down by minus 0.4. And that tells me that the value X in the table would be minus 0.4. You should also be aware that chemical cells can be wired together in series to produce a battery, and we do this to produce a battery that has greater voltage, so therefore it's more useful. We know that in non-rechargeable cells and batteries, the chemical reactions are going to stop when one of the reactants have been used up, and alkaline batteries are an example of a non-rechargeable battery. Then in contrast to that, rechargeable cells and batteries can be recharged because you apply an external electrical current and therefore reverse the chemical reactions. Fuel cells are quite different to chemical cells and batteries. So whereas a chemical cell or battery has a finite supply of fuel that you have and then you use and that generates current and then it's gone, with a fuel cell you're continuously supplying an external source of fuel. And hydrogen fuel cells are a very, very common example of this. So in the hydrogen fuel cell, the hydrogen is oxidized electrochemically. So what that means is we're not actually heating it up and reacting it with oxygen, which would release a huge amount of energy, but in a very inefficient way and would also be quite dangerous. Instead, we've got this electrochemical process going on. So the hydrogen comes in and it's split up into hydrogen ions and electrons. So it's lost electrons, so that's oxidation. And then the electrons are flowing through a wire, while the hydrogen ions flow through the electrolyte. And on the other side, oxygen comes in and is used, it dissolves in water and it picks up electrons and it produces hydroxide ions, and those hydroxide ions join up with the hydrogen ions to make water. So overall we have this electrochemical process where hydrogen is oxidized and the only waste product is water. However, it's worth being aware that at the moment there are only two real ways of getting the hydrogen to use as a fuel, and neither of them is particularly good for the environment. Either you electrolyse water, which needs a huge amount of energy, or you react methane with steam, which is using up a fossil fuel. Describing what's going on in a fuel cell can be quite challenging, particularly if you have a chemistry teacher who has taught you the panic rule for electrolysis, because panic is good for naming your electrodes for electrolysis, but it's completely backwards for fuel cells. So you've got two choices. Either you remember that everything's backwards, or you don't learn that rule in the first place, and instead you learn that reduction happens at the cathode and oxidation happens at the anode. So in fuel cells, our positive electrode is going to be the cathode, because the positive electrode is where the electrons are being given up, and then the negative electrode is at the anode, because the reason it's negative is that it's taken all of those electrons that have been given up by the hydrogen when it was oxidized. And you do need to know your half equations here. So the one for hydrogen is quite straightforward, and then the positive electrode is a bit more complicated. It might help you to remember that it's the same one that you use in electrolysis for hydroxide ions being discharged, just backwards. And then finally, you might be asked to evaluate and compare the use of hydrogen fuel cells versus rechargeable chemical cells. So hydrogen fuel cells are continuous, we're pumping in hydrogen fuel all the time and they can just keep going and going, whereas rechargeable batteries are going to run out and need to be recharging. And so that means that hydrogen fuel cells maintain their efficiency the whole time, whereas rechargeable cells gradually get less and less good the more you use them. So if you think about your phone battery and how when you first got your brand new phone, it lasted for ages, but by the time you're ready for a contract upgrade, it's not even lasting the whole day. Hydrogen fuel cells, the waste product is pure water, but rechargeable cells may have heavy metals in them which may be toxic. That hydrogen is highly explosive, whereas rechargeable cells, the fuels aren't really very dangerous. And hydrogen fuel cells have a relatively low potential difference, so we need to wire several of them together to make a battery, whereas rechargeable cells have a larger potential difference. Thank you very much for watching, and I hope you're now feeling a bit more up to date with everything that is in Chemistry Unit 5. Good luck for your exams, and if you did find this video useful, don't forget to like, subscribe, comment and share for more GCSE Science revision videos coming soon.